Let's have a look-see at the new Milwaukee Brushless M12 battery-powered rotary tool. We're going to compare it to the venerable Proxxon IB mains-powered rotary tool. This one, for a little bit of a caveat, it's a slightly outdated model. They got a new one which is basically identical. However, the new one has an extra bearing up at the nose end, supposedly helps with runout. Yeah, that's an improvement, but a disimprovement is that the new one uses overmolding rather than this nice rubber insert. Anyways, for this video, I'm going to divide it into three different parts. The first part, I'm going to look at the overall form factor of these tools and, most importantly, ergonomics. Secondly, I'm going to tear them down and take a look at their insides and discuss their operating principles, brushless versus brushed. And then thirdly, I'm going to run some tests on them, see how fast they go, see what their speeds are like, see how much power they draw, and see how they operate under load. Well, let's get to it. Ergonomics first. Rotary tools, they're meant for nuanced and detailed work. They're held for long periods of time, so ergonomics is a prime concern. Now, while I'm not unacquainted with the tool of such girth, rotary tools really are better off thinner. Now, neither of these could be considered as svelte. However, the Proxxon is noticeably thinner. Let's take a measure of it. And in width, it's around just a little under 2 inches wide, and by about 1 3/4 of an inch. In comparison, this Milwaukee is around a little bit thicker at about 2 1/8 inches in thickness, and it's in about both dimensions. Yeah, so this one here is definitely thicker and a little bit more difficult to handle, in my opinion, compared to this Proxxon. Now, in length, the Proxxon is about less than 9 inches, while the Milwaukee is about 10 inches with the battery included. So this is going to have a little bit more of a moment arm when you are handling it relatively close to the bit end. There's going to be a bit of a weight pulling you back. Well, this Proxxon is not immune to that. There's actually a cord here dangling, and that might be a problem, might not be, depending on your setup. Now let's take a look at their weights. Let's start off with the Milwaukee with a CP 2.5, their new high output bat. That's what they recommend. You get 572 grams. Now compare that to this Proxxon, and the Proxxon is 456 grams. Add a little bit of cord to it. Maybe 460 grams of weight. It's 100 grams lighter than this Milwaukee. However, really, this Milwaukee does not too bad. Proxxon does make a battery-operated model, an equivalent to this IBE. However, it's considerably longer, and I think it weighs somewhere around 800 grams. So this Milwaukee doesn't do too bad for weight. Now, let's take a look at how we handle these tools. Well, you might just choke on it like this if you're doing some sort of grinding or sanding or something like that for long periods of time. This chokehold grip, it's definitely easier when it is a narrower tool. This Milwaukee's noticeably girthier in that regard. However, let's talk about nuanced work. The Milwaukee product literature shows this rotary tool being used like a pen. They put their hand down like that, and that just is really uncomfortable to me. And again, this big ass end battery is it's like a moment arm, and I can't imagine using this tool for long periods of time like this. Let's take a look at this Proxxon. It has a bit of a different design. Let's compare them in side view, and you notice in side view there's a bit of a dipsy doodle here on the dorsal side of the Proxxon, where the dipsy doodle on the Milwaukee is on the ventral belly of the beast. What's that all about? Well, I figure that this Proxxon, the way you use it, is not like a pencil, but with this sort of a grip right here. A thumb can rest on this rubbery grip, and your fingers wrap around and press in on this little dipsy doodle. And you get a really good grip like that, and the vents are open. Now, what I figured out with this Milwaukee is that you can do the same thing. Rather than holding it right side up, hold it upside down, and you get basically the same effect. Notice that when it's being held like this, the vents are completely unobstructed, so you can use the tool for long periods of time, and you don't have to worry about it overheating. Yeah, compare that to this here, this pencil mode, and well, you're going to be blocking those vents. So yeah, I think that pencil mode is more for the marketing people at Milwaukee rather than actual users. Now let's take a look at their overall form factor. This Proxxon model, it doesn't have overmolds, the older one anyways. Really nice rubbery strips that are inserted into this plastic housing. A really interesting design in that this Proxxon is radial. It's not a clamshell that has a plastic joinery in the middle. Those are really annoying, especially if you're like doing a chokehold on it or something like that. It can be irritating on the hand. This radial plastic, notice that there is no molding mark. There's no place where the plastic has come together. Instead, this butt end is screwed with these really long screws into the metal housing up at the front. Pretty neat. Die-cast metal at the front, and not this sort of rubbery grip on the Milwaukee, but I do find that it has a very, very secure feel in use. Some obvious things is that the switch is a nice, easy to operate switch and a easy to operate dial control. I have on occasions accidentally turned this on and turned it off in use. It is really easy to actuate or to deactuate. Now, in contrast, this Milwaukee does use a typical clamshell construction where there are two halves that are screwed together. However, it's done pretty well. There's no little line really that's going to dig into your skin when you're using it for a long period of time. This rubber overmolding, actually, it's really quite well done. A little bit different for the operation. Instead of a easy to actuate switch, there you go. It's a slider, not entirely easy to actuate, in my opinion. I do find I get a little bit of a divot in my thumb whenever I actuate it. Yeah, so it has that switch up at the front. Nominally, it's going to make it so that you don't accidentally turn it on or turn it off in use. But to be honest, I think I kind of prefer the easier to actuate model. Now, a lot of people are complaining about the speed control using these little buttons. While it is definitely slower than just turning a dial, I kind of like it. It doesn't bother me. In fact, sometimes these digital controls are nice because if you have a particular job, a particular bit that you're using, that you know what speed does the work, and that way you can come back and you can just dial it in with the buttons you know is 3.5 or something like that. Yeah. So anyways, that's the operating principles of these machines. Now let's take a look at the bit affixment. Here's the collet up at the front, and on the Proxxon there's a little metal locking button. And when you need to take a collet off, you grab the collet wrench. Nice, comes with equipment, and it's nice, and you can slip that over, and you can do that, and then you can promptly lose that one. Yeah, not bad. I do find this little metal divot's kind of, again, it kind of digs into my thumb a bit. It's not super ergonomic, and the this collet at the end, it doesn't offer a lot of purchasing power for taking it off by hand. Now, in comparison, Milwaukee has got this famous, well-known now, this built-in collet wrench, which is kind of cool. You notice you can take it off, and it's got threads here for fitting Dremel attachments. Now, in contrast, this Proxxon isn't threaded. Instead, it has this European standard smooth nose. The Proxxon does have a number of accessories that will fit this. Won't fit Dremel accessories, however. On the Milwaukee, the collet lock is a button here, and it's definitely easier to actuate, not as digging into your thumb, and the collet is much, much easier to open and close, tighten, and then untighten by hand. Yeah, I kind of like that one a lot better. Now, turning to the rear of these tools, the Milwaukee will accept any M12 battery. You can put in a larger one if you like. And I noticed something interesting with this tool. Can you see that little rubber bumper in there? Yeah, people have been complaining about Milwaukee M12 batteries sliding out. And it seems that rubber bumper is to hold that battery in extra securely. Kind of a neat addition, though I do find it really does make getting the battery in and out a little bit tougher. On this Proxxon, well, you got a wire at the cable at the end. Moderately flexible. Now, this Milwaukee doesn't come with any sort of storage option. However, the Proxxon comes with a really excellent storage case, blow molded. And inside there is a little bit holder that you can take out. I don't use it. I keep my bits elsewhere. And it comes with a full set of collets. This Milwaukee, if you want to get extra collets, you got to pay extra for them. Yeah, this case is really awesome because you can throw the Proxxon in there, and there's so much space for the cable. You just jumble it in there like that, and where did that come from? Just jumble it in there like that, and the net effect is that you don't end up with memory in the cable. The cable is nice and stretched out, and it's not all kinked like those blow molded cases where you have to wrap the cable up really tightly every time to get it put away. Okay, let's tear them down, see how they're built, see how they work. We can do a bit of a comparado. Let's first of all start off with this Milwaukee. This Milwaukee is typical of any modern plastic fantastic power tool in that it is highly engineered with lots of ribbing and detail for packing all the components in there really nice and tightly. Yeah, this is designed well to handle a little bit of abuse. I fall off a ladder and hopefully not get broken. Made out of some pretty decent plastics. It's glass-filled nylon. Not sure that's registering there. Otherwise, I'm not going to say much more about this encasement other than I'll point out that rubber rubbing battery holding stabilizer, whatever thingamajig. Now, let's contrast that with the Proxxon. The Proxxon has a die-cast metal head, and I'm not going to take this apart. It's all press fit, and it's not that interesting anyways. The bearing in this mechanism, the fan there. Now, the casement is this plastic radial shell. Like I said earlier, it's not a clamshell. And it's much simpler inside without any ribbing. There's no indication as to what type of plastic it is, but it really does feel quite rigid. So it's some sort of good quality material. Just by its texture and its look, it kind of looks like the Milwaukee glass-filled nylon, probably. Now let's turn to the internals and start off with the Milwaukee. Here's the speed control, the battery terminals, a fuse, computer board, power switch, and where the action happens, and we have that brushless motor. LED. That brushless motor, it's not a fuel motor, however. Fuel motors, as far as I'm aware, they are proprietary Milwaukee technology. I do believe that they use red plastics, not black like this. My guess is this is some sort of off-the-shelf or made by some factory other than Milwaukee ordered, and then they stick them into the power tools. And they don't label them fuel. Anyways, this brushless motor is very cool because, well, there's no brushes. Let's compare it to this Proxxon motor, which is a brushed motor. You can see in here commutator bars, and these commutator bars are what take the electricity here. It's a positive and negative, so it's a DC motor. Take that electricity and they energize the coils that are on the armature or the rotor that spins. Now the problem with that is that armature can only be so large. The coils, I'm not sure whether it's visible in this view here, but the gauge of the wire is fairly thin, and there's not nearly as much copper in this motor as in this brushless motor. In a brushless motor, the rotor is the permanent magnets, and the stator, you can see much higher gauge, thicker gauge wire to energize the system. So the way it works is a computer and a circuit board here underneath all this elastic. Well, it's deciding how to energize these coils, and what's actually energizing them from the battery, the current goes through some high-speed, high-current switches. And it goes to 3 wires. So it basically imitates 3-phase, and in 3-phase what it does is it energizes these coils in a rotary sort of a fashion, and that's what's going to cause that the rotor inside to spin. The magnets are going to, well, they're going to be interacting with the field generated by these electromagnets. Now, in contrast, this brushed motor, well, the commutator is going to determine what coils are being energized on the rotor, and the rotor is going to spin, and then another commutator bar is going to get energized. Well, we're going to energize another coil, and that's how that motor works. So this is a much more sophisticated system because a computer is in control. A computer is determining how to make this motor work. Now, part of that system are these sense wires, and these sense wires are attached to sensors that detect just how quickly this motor is spinning. And they're called Hall effect sensors, and they detect the magnetism as it's passing by each sensor. So what the computer can do is it can determine when there's a load being put on this motor. A load's put on, so the speed slows down, and the computer can operate a negative feedback to maintain the speed, to keep the speed up. Yeah, so it's a much more sophisticated system, and back again to these coils and these thick wires, they are able to handle a lot more current, hypothetically, compared to a brushed motor. Now this Proxxon, in comparison, it has a much simpler system for controlling this motor. Here's the circuit board. We got a potentiometer here, a handful of capacitors, a handful of diodes, and we have a triac. So how this works is AC power comes in. These 4 diodes rectify that AC power and they turn it into pulsed DC. The pulsed DC is fed to the motor, but one line to get to the motor, it needs to pass through this triac. And this triac is basically a very, very high-speed switch. And what it does is it switches on only during certain parts of the pulse cycle. And how much of the pulse is being turned on is determined by this potentiometer and a few other circuit items here that determine when this triac is firing. It's a pretty simple system, but it is effective. The way it works is that the motor's voltage increases. The voltage across these 2 lines, the positives and negatives, increases when the motor is operating nominally without a load. Now, when a load is placed onto this motor, the voltage across those 2 lines, the motor voltage, it decreases. And when the motor voltage decreases, this little circuit feeds that lowered voltage into the gate of this triac, and that makes the triac fire more. So it gives the motor more current, and that, hypothetically, will maintain the motor speed. Okay, I got my oscilloscope set up. Don't laugh. It's hooked up across the motor so that we can see the operating principle of this motor control circuit. Let's turn it on. And on the screen, we can see a DC voltage. That's the motor voltage. We also can see the spikes, and that's part of this high-speed electronic switch, the triac, in its operation. It's getting turned on every, what would be 120 times a second. Now, I described earlier that when this motor is under load, this triac is going to be switched on more. When the motor is under load, the voltage is going to decrease, the motor voltage will decrease, however the triac will turn on in an attempt to compensate. And we can see that right there. See the motor voltage go down, spikes go up. Yeah, it's an effective speed control mechanism. Basically, all variable speed power tools, mains powered, use some sort of a system like that. They only have one little catch, and the catch is if the motor voltage goes down, that's if we stall the motor. What's going to happen is that triac is going to be turned on all the time, letting mains current flow through the motor and through these components. Something will let the smoke out. Now, in contrast, this brushless motor and its control are much more robust against burnout. Once again, how it works is that the computer senses how fast the rotor is moving. If the rotor slows down because of load, it ups the juice into the coils. However, if the shaft completely stalls, well, the computer will understand that, and at least hypothetically, it'll cut power to the coils entirely and, well, save everything. At least that's the idea. We're all together again and ready to do some testing. To see how fast these things are spinning, I got an inexpensive eBay tachometer. To see how many watts this Proxxon is consuming, I have a kilowatt. And to see how much power this Milwaukee is drawing, I have an M12 line splitter that I built some time ago, and I can put a clamp on meter and see how many amps this thing is consuming. And to test these tools under load, I got a 2-inch cutoff wheel and a hunk of scrap steel, like a 1/4 inch thick, held in some heavy pliers. and I'll be able to apply that to this cutting disc with close to 500 grams, a little more than a pound of force. All I need now is a testing rig. And here's the setup. I had RPM, I got amps, I got a fresh 2.5 battery in. I have no load, just a mandrel to keep the collet nice and tight. Let's try it at the lowest speed. At the lowest speed, the computer-controlled motor does a really good job of maintaining RPM. It's really close to marketed specs of 5,000 at the lowest speed setting. Power draw looks like around 0.3 of an amp. Now let's turn it up one step at a time and see what happens to current and see what happens to RPM. Speed number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and maximum. 2.4 amps, 27,500 RPM. Let me turn that down. And let's now test the performance under load. Use the handy dandy collet wrench to take off this mandrel. Stick on the cutoff wheel. Tighten it up. And I'm going to test it at its lowest power, because it's at the lowest power that the motor control is going to have the most difficult time in maintaining speed and maintaining power. At higher speeds, well, it's the speed that does the work, but at lower speeds, that's where you want the torque. So recall, this is going to be up to about a pound of force being applied up to 7 amps of power. However, this tool did a remarkable job of maintaining speed. Okay, now let's put the Proxxon through the same paces. I got it hooked up to the mains through the kilowatt. I got it at its lowest speed. Nominally, it should be 5,000 RPM. And it's not 5,000. It's actually closer to 7,000 RPM. My guess is that this motor loads fairly easy and the speed goes down. At its lowest setting, is drawing a little more than twice the power that the Milwaukee draws. The Milwaukee was drawing around 4 watts of power. Now let's ramp the power up to maximum. Maximum is supposedly 20,000 RPM, and see what it actually does. About 21,500 RPM. The power that was being drawn was about 35 watts. This Milwaukee, in contrast, at its highest speed, it was drawing about 28, 29 watts of power. These brushless motors are supposedly a little bit more efficient. We'll have to see what happens when we put this Proxxon under load. So we're going to do the same thing that we did with the Milwaukee. Let's take this mandrel off and stick on the cutting wheel. That built-in wrench in the Milwaukee really is actually quite nice. This isn't too bad though. Okay, now just like the Milwaukee, I am going to do this at the lowest speed. Now let's pay attention, and I'm expecting that this is going to drop a lot further, and that's going to go up quite a bit. And here we see that the motor bogs down really quite strongly, well under 3,000 RPM, and the power draw went up well above 100 watts. At the highest, the Milwaukee was drawing a little under 100 watts of power, and yet it maintained its speed about 5,000 RPM throughout. These brushless motors are pretty amazing, really. One more test. Let's see the noise level. If you're right-handed, I'll change your earbuds from one ear to the other. Okay, at low speed, the Milwaukee, about 75 decibels. At maximum speed, it was about 94 decibels. Proxxon, 68 decibels. And about 86 decibels. This is definitely a little bit easier on the ears than the Milwaukee. Let's conclude by answering the question that everybody wants to know. What's better, the Milwaukee brushless or the Milwaukee brushed? Well, for that, I don't really have an answer. But I can compare this Milwaukee brushless versus this Proxxon, and this Proxxon will have some things in common with that Milwaukee brushed. It's a brushed motor. The motor control system will be a little bit different, but more similar to this Proxxon than it is to this new brushless. This brushless does have awesome performance at lower speeds. If you really like your battery portable usage, if you're going to be using cutoff wheels, wire wheels, buffing wheels, yeah, this Milwaukee will be really ideal for you. But if your work is mainly at your bench and you got an outlet handy and the cord's not going to be in the way, this Proxxon does have its virtues. It's way more ergonomical, and really at the highest speed settings for smaller bits, you don't need that much power anyways. It's the speed that does the work. Well, anyways, thanks for watching. Hope you found that informative.